Hello everyone, welcome to the course on design of reinforced concrete element. In this section, we are going to see about the different types of RCC beam sections. The beam sections are classified like balanced, over-reinforced and under-reinforced section. The first one is a balanced section. The balanced section means in which the stress in concrete and steel reach their permissible value at the same time. So the first figure for the balanced sections. Here this is your stress diagram. So balanced section, both materials, stress in steel and stress in concrete reaches simultaneously. At the same time, the maximum stress in concrete and maximum stress in steel or reaches at the same times. This is considered as a balanced section, and the percentage of steel corresponding to this section is called as a balanced steel. And the neutral axis is called as a corresponding neutral axis is called as a critical neutral axis. This is a critical neutral axis denoted by NC. And the neutral axis we can write like that. So this is the stress diagram. The maximum stress for concrete sigma CBC, in steel sigma ST by M. So this is the neutral axis NC. NC. The remaining distance is we know that D minus NC. This distance is effective depth minus NC. So from the similar triangle concept, we can write these equations. Sigma CBC divided by NC equal to sigma ST by M divided by D minus NC. So rearranging this term, we can get these equations. M times of sigma CBC divided by sigma ST, NC divided by D minus NC. For balanced section, the moment of resistance is calculated as under. The both materials are both materials are reaching their maximum stress at the same time. So moment of resistance equal to sigma CBC divided by 2 area of the stress. So area of the triangle half into B into H. So multiplied by the B into N is written as NC because we called as a critical neutral axis, and multiplied by the lever arm D minus NC divided by 3. Similarly, the both materials are failed at the same times. So moment of resistance due to concrete and moment of resistance due to steel, sigma ST, AST and lever arm D minus NC divided by 3. So this is considered as a compressive force. In the previous session we are discussing C into lever arm. This is a T into lever arm. Compressive force into lever arm, tensile force into lever arm. Already we have discussed about it, and both compressive force and tensile forces are acting at both are in opposite directions. So the resultant compressive force is act at a distance of NC divided by 3. So up to this is a neutral axis. This distance is called as NC. So the remaining distance is D minus, this distance is, the lever arm means the distance between the compressive force to tensile force. So N divided by 3 already we have discussed in the previous session. Next, under-reinforced section. In under-reinforced section, the percentage of steel provided is less than that provided in the balanced section. So provide AST is lesser than the provided in the balanced section. So the actual neutral axis will shift upwards. NA is lesser than the NC. NA is lesser than the CC. We can see this from this diagram. Under reinforced sections, the first the steel reaches their maximum value compared to the concrete. So actual neutral axis is lesser than the critical neutral axis. This is your actual neutral axis. NA is lesser than the NC. The first, the maximum stress reaches at the steel. So the actual neutral axis will shift to the upwards. So NA is lesser than the NC. In under reinforced section, the stress in steel reach first its permissible value, while concrete under stress. This is lesser than that sigma CBC. Sigma CBC is a maximum permissible stress, but this stress is lesser than that sigma CBC. Only the stress in steel only reaches its permissible value before reaching the concrete. So the moment of resistance of this section is calculated sigma ST AST D minus N divided by 3, because the moment due to the steel we have calculated. So tensile force into lever arm, T into lever arm. Various features of under reinforced sections are as follows. The steel fully stressed while concrete not. Concrete is the permissible the stress in concrete is lesser than that sigma CBC, but the steel fully stressed while concrete not. The stress in steel sigma ST is permissible, but stress in concrete is less than the sigma CBC. So the actual neutral axis lies above the neutral axis, critical neutral axis. The critical neutral axis is the both materials are reaching simultaneously. This is the neutral axis. But in this case, the maximum stress reaches in the steel only, none for the concrete. So connecting these diagram, sorry, this. This is the actual neutral axis for this case, NA. This is a critical neutral axis, NC. So NA lesser than the NC. So the neutral axis is shift upward directions comparing to the critical neutral axis. So NA is less than the NC. The percentage of steel is less than the balanced section. Hence, this section is considered as economical. And ductile failure. Ductile failure only happened in this section, under reinforced section. The moment of resistance is lesser than the balanced sections. In under reinforced section, the failure is here ductile because the steel fails first and sufficient warning is given before the collapse. So during the earthquake, the occupants will be easily escaped from the buildings. So due to the ductile failure and the economy, the under reinforced section is prepared by the designers. The next section is over reinforced section. In an over reinforced section, the percentage of steel is provided is greater than the balanced sections. So the AST is greater than the AST for the balanced section. So in this case, the actual neutral axis shift the downwards. So in this case, this is your critical neutral axis. Critical neutral axis for the balanced section. This is for the actual neutral axis for the over-reinforced. So NA is greater than the NC. For in this case, maximum stress reaches in the concrete. This is maximum stress. So sigma CBC, maximum stress reaches in this concrete, but in steel is lesser than the sigma ST by M. The steel not stressed like that, like concrete. So in this section, stress in concrete reaches its permissible value while steel is not fully stressed. So according to the failure first will taken by the concrete. So the moment calculated based on the uh, permissible stresses in concrete. So the moment of resistance equal to C into compressive force into lever arm. The compressive force already we know that area of the stress diagram half into B into H and multiplied by the yeah, B breadth of the section and lever arm D minus N divided by 3. Concrete is brittle in nature and it fails by crushing suddenly as steel is not fully utilized. So this section is an uneconomical, and because the steel is much costlier than the concrete. So this is an uneconomical. At the same time, during the earthquake, the peoples cannot be escaped from the buildings. It does not give the any time, any warning to the people. So this is not prepared by the designers. Only under reinforced concrete only prepared by the designers. The various features of over-reinforced sections are as follows. The concrete fully stressed while steel is not. So stress in concrete is permissible value, reaches its permissible value, but stress in steel is less than the sigma ST. So actual neutral axis is lies below the critical neutral axis. Actual neutral axis is below the critical neutral axis. So Na is greater than the Nc. The percentage of steel is more than the balanced section. Hence, this section is uneconomical and this section's sudden failure only happen. The next one, problem. The second problem. Find the moment of resistance of a RCC beam 300 mm wide and effective depth is 500 mm. Find the moment of resistance of your RCC beam 300 mm wide and 500 mm effective depth. So this is the effective depth, center of the reinforcement. This is the effective depth 500 mm is reinforced with 3 bars of 16 mm diameter, M20 grade of concrete and Fe 415 steel is used. Solution. For M20 grade of concrete, refer the table 21, page number 81 in IS 456 2000. For Fe 4 and 5 steel, table 22, refer the page number 82 in the IS 456. Table 21, permissible stresses in concrete is given in the IS 456 2000. Permissible stress in concrete in compression due to bending, due to direct compressions is given in the table 21. Permissible stress in concrete. The page number 81. So sigma CBC values are given for the different grade of concrete for M10, M15, 20, 25 up to M50. The sigma CBC value is given due to that bending, sigma CBC, direct compressive stress in compressions due to bending, due to direct. So sigma CBC values in our case for M20 grade of concrete, for sigma CBC equal to 7. Sigma CBC equal to 7 Newton per mm square. Similarly, the permissible stress in steel reinforcement is given in the table 22, IS 456, page number 82. So tension up to the 20 diameter rod for mild steel is 140 and 130. Beyond that 20 sigma is equal to 130. And here this is for medium tensile steel. In our problem, HYSD bars, we have to consider say HYSD bars. So for high yield strength deformed bars, up to 20 sigma ST equal to 230. Sigma ST equal to 230. Sigma ST equal to 230 Newton per square. M equal to 280 divided by 3 into sigma CBC. Sigma CBC value equal to 7. So a modular ratio equal to 13.33. And breadth of the sections, we know that 300 Effective depth 300 breadth of the section. Effective depth is 500 not your overall depth of the sections. AST is given in our problem. AST equal to 3 times of pi d square divided by 4. So 16 dia. The AST is provided 603.42 square. Critical neutral axis. From the stress diagram, based on the similar triangle concept, M into sigma CBC divided by sigma ST equal to NC divided by D minus NC. We want to calculate the critical neutral axis. So after substituting the value of M 13.33 multiplied by the 7 divided by 230 and NC is the unknown value. NC divided by D minus NC. D is the effective depth. So 500 minus NC. Solving these equations, we can get NC equal to 144.13 and actual neutral axis calculated based on the moment of compressive area equal to moment of tensile area. This is a compressive area. So B into N divided by 2. So B N square divided by 2 equal to M times of AST D minus N. D minus N. This is your up to this neutral axis N. The remaining distance is D minus N. So moment of compressive area. So B into N multiplied by the centroid. So N divided by 2. B N squared divided by 2 equal to M times of AST and D minus N. Then substituting the value of breadth of the section equal to 300 and multiplied by the N squared or NA actual neutral axis divided by 2 equal to M times of 13.33 multiplied by the 603. Area of the reinforcement is 603.42. 603.42 and the effective depth is 500. Effective depth is 500 minus of N. So solving these equations, this is an quadratic equations. So solving this equation, we can get the two values. So based on that, N equal to 139.13. So the actual neutral axis is 139 and critical neutral axis is 144. So comparing, the next step is comparing the critical and the actual neutral axis. So NA is lesser than the NC. NA is lesser than the NC. Critical neutral axis is below the actual neutral axis. Hence, the beam is under reinforced. Under reinforced means the moment of resistance of the beam will be calculated based on the steel only, because in the case of under reinforced, the steel failed first. So moment of resistance equal to sigma st AST T into lever arm. That's all. T into lever arm. Tensile force into multiplied by the lever arm. Lever arm is D minus N divided by 3. N divided by 3. So N is here the actual neutral axis. Actual neutral axis. So substituting all the values. M sigma ST equal to 230 and AST equal to 603 and effective depth 500 minus of actual neutral axis 139 divided by 3. So solving this one, moment of resistance equal to MR equal to 62.95 kilonewton meter. 62.95 kilonewton meter. These are the exercise problem. You will try to solve the problem in the classrooms. Next, multiple choice questions may be asked from this this content. From the based on that working stress concept, these questions may be asked. Modular ratio is given by, there are four options are there. 280 divided by 3 into sigma CBC, 285 times of sigma CBC, 280 divided by 3 times of sigma ST. So from this, this is the right answer. 280 divided by 3 into sigma CBC. 280 divided by 3 into sigma CBC. And the next one is, the depth of actual neutral axis is more than the critical neutral axis. The depth of actual neutral axis. Actual neutral axis. This is the critical neutral axis. Critical neutral axis means this is considered as a balanced section. So both materials are failed at the simultaneously. This is a critical neutral axis. This is the actual neutral axis. Actual neutral axis. Actual neutral axis is more than the critical neutral axis, means this is considered as a over reinforced section. So over reinforced sections, the concrete will be failed. Concrete stresses reaches its permissible values. So sigma CBC. This is sigma CBC, but not fully stressed for the steel materials. So depth of neutral axis. This is the depth of neutral axis is move the downward directions. So actual neutral axis is more than the critical neutral axis, means over reinforced section. This is the correct answer. Over reinforced sections. Design constant K, J and R depending upon the grade of concrete, type of steel, A and B, none of the above. Actually K equal to 280 divided by 3, 280 divided by 3 plus sigma ST. See, it is depending upon the steel, grade of steel. And J equal to 1 minus K divided by 3. K is depending upon the K value, 1 minus K divided by 3. R equal to 1 by 2 of sigma CBC and K times of J. So both steel and sigma ST is a steel and sigma CBC are grade of concrete. So the answer is grade of concrete and type of steel. The next question is the value of factor of safety for concrete. Value of factor of safety for concrete due to bending compression is 3, due to direct compression is 4, but not mentioned due to bending or due to direct compressions. One is given, 3 value is given. So due to bending, the factor of safety for concrete as per the working stress concept is 3. For steel is 1.78 as per the working concept. The factor of safety for steel is 1.78 and concrete is 3. The next question is, the moment of resistance of an over-reinforced section is equal to the balanced section, less than the balanced section, more than balanced section, less than under-reinforced sections. More than the balanced sections, because AST provided for the over-reinforced section is more than that AST provided for the balanced sections. So the AST is higher. So the moment of resistance also higher than the balanced sections. The next one is in under-reinforced section. In under-reinforced section, the AST is lesser than the balanced section. So the first one is, this is for concrete stress. This is for steel, sigma ST. So concrete is fully stressed, steel is fully stressed. For under-reinforced section, the steel is first failed. Steel only reached their permissible stresses. The maximum permissible stresses reached steel first. So the answer is the steel is fully stressed. The next one, 7th question. The neutral axis of a balanced section is called as actual neutral axis for the balanced section. The balanced section, the both materials are steel and concrete are reaching the simultaneously, reach their permissible value at the simultaneously. So this neutral axis we call as a critical neutral axis. Critical neutral axis. Fe4 and 5 steel, the permissible stress is 250 megapascal, 150 megapascal, 230 and 200 megapascals. So already we have discussed and referred from the table, page number 82, the sigma ST value is 230 up to the 20 mm and more than 20 mm also sigma ST is the same value. So this is the right answer. The next question is, moment of resistance of a balanced section is given by, moment of resistance we can calculate both concrete and steel because both materials are failed at the simultaneously. So the moment of resistance due to concrete, moment of resistance due to steel we can calculate. Here the 4 options are based on the only grade of concrete only. So the answer is half into sigma CBC stress and multiplied by the area and lever arm. So C compressive force into multiplied by the lever arm. This is not wrong answer. This is also not multiplied by the depth, not multiplied by the depth. So breadth of the sections and depth of neutral axis and D minus N divided by 3. So compressive force is multiplied by the A. The next one is K is called as actually N equal to K times of D. So N is a neutral axis. So K times of D, K is